The first ionization enthalpy values in kilojoules per mole of group 13 elements are tang, 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 tang. How would you explain this deviation from the general trend? Now, this is a very striking data and a very interesting graph. If you care to plot it, you would find boron is the highest, yes, with 801. And then you have aluminium, tarizami par, right? Gallium is very slightly, very slightly higher than aluminium. Just allow me to make a reference line so that, we can do it again properly. Gallium goes very slightly up, yeah. Barely 2 kilojoules per mole, but it's significant. And then indium further dips down. And then, shamelessly, thallium shoots up. It's a kind of ting tang like this. There are two dips at aluminium and indium, or rather, it was anyway down the group, it was supposed to come down, so that's okay. Abnormalities actually lie when you talk about gallium and thallium. This gallium-thallium is a dangerous business, and the question is, why does this anomaly happen? Why is it that gallium and thallium, which would have been probably, you might have expected them to be somewhat like this, they just go up from their regular values? Why should we expect this? And how do we explain this deviation of gallium and thallium from the general trend? General trend is down the group it should decrease. It is decreasing for boron, aluminium and indium. Problem is with gallium and thallium. How do we explain this? The explanation lies in, well, the appearance of D block and F block for the first time. In case of thallium, it is what is called as lanthanoid, like a lanthanoid contraction. Just look at their atomic number once. Boron has atomic number 5. Aluminium is 13. 5 plus 8, 13. So there is an increase in one shell. This is boron has 2 electronic shells, aluminium has 3. And atomic number goes up by 8, which is fine. From aluminium to gallium, gallium has atomic number 31. Only one extra shell is added. From aluminium to gallium, only one extra shell is added, but atomic number or nucleus charge increases by not 8 but 18. There is a sudden jump from 8 to 18. So nuclear charge increases substantially. Instead of 8, it has gone up by 18, out of which, you might say that if nuclear charge goes up by 18, we are also adding 18 more electrons. Yes, but out of those 18, 10 electrons are added to D subshells. And D subshells are not very good when it comes to protecting the nuclear charge or screening the nuclear charge from outermost electron. What does that mean? It means that the nucleus of gallium will now attract the outermost electron more strongly. Why? In spite of having one more shell, like aluminium has 3 shells, gallium would have 4 shells. Fine, one more extra shell added. But because nuclear pull is so strong, it has taken the electrons inwards. As a matter of fact, radius of gallium also is somewhat shorter than aluminium. It is closer to nucleus, it is attracted more strongly by the nucleus of gallium, and that is why ionization energy of gallium becomes somewhat higher as compared to that of aluminium. The same factor becomes much more pronounced in thallium. Why? Gallium to indium, this is 49, and now thallium is 81. Oh my God. There is a sudden jump from indium to thallium. Nuclear charges increases not by 18 but by 32. Wow. 32 extra electrons, protons are added to the nucleus. So 32 extra electrons are also there, but out of which 14 are added to 4f subshell. D electrons were not good at screening, right? F subshells are even poorer when it comes to screening the nuclear charge. That means they cannot keep the extra nuclear charge away from outermost electrons, outermost electrons are now attracted more strongly towards nucleus in the case of thallium, and that is why the size of thallium also is not as high as it was expected to be. This feature is also attributed to a phenomena called lanthanide contraction. After lanthanum in F block, you find all the lanthanides have continuously and very successively decreasing radii, because of which you find second and third transition series elements in D block have roughly similar radii after lanthanum. What I mean is, except group 3 and 4, if you take groups later on, 5 to 12, you find that second and third transition series have roughly the same radius. Why? Because nuclear charge has increased, but the extra electrons which have been added are not able to screen that extra nuclear charge. So you find a greater attraction of outermost electron by the nucleus, and that leads to an increase in ionization energy, because nuclear charge is now attracting outermost electrons more strongly. It is attracted more strongly, so ionization energy naturally increases. So these are the features. I mean, if I just summarize this in one sentence, you might say, what do we write down? What we write down is this: in case of gallium and thallium, nuclear charge increases by 18 and 32 respectively, right? The extra electrons are added to D and F subshells, which are not very effective in screening the nuclear charge against the increased number of protons. Because of greater nuclear pull on outermost electrons, the ionization energy increases.